Hi everyone. Um, this is an additional problem solving session for the course Introductory Field Structural Geology offered by NPTEL. So we have already covered the live sessions for the past 4 weeks, which is the normal curriculum for this course. However, in addition to the existing 4 week live sessions, we are also hosting another problem solving session for your doubts. If you have anything to clear regarding the course, and if not, then we will further discuss something which was not mentioned in the course but might seem valuable for understanding field geology in that perspective, especially structural field geology. So we will be having these kind of discussions today. So my name is Rajiv Mukherjee and I am a Prime Minister's Research Fellow at the Experimental Rock Deformation Laboratory of the Department of Earth Sciences, IIT Kanpur. So, um, so if I now talk about what we have learned in the entire duration of these introductory field geology course, so the course outcome we can highlight several points. So first of all, how to interpret a geological map, and most importantly, while going to the field for the first time, when you see some exposures, so looking at the exposure from a larger scale, or we shall say that from a bird's eye view, we have to look into the region, what kind of structures we are getting if we look from above or a very zoomed out version of the area. So that is why understanding a geological map, even if you do not have any geological map, just by looking into the Google Earth view of that location would give you some information about the topography. First of all, whether it is a rugged terrain or a flat terrain or a hilly terrain, right, like. So apart from that, if there are some undulations in the topography, then how these geomorphic feature could be related to a structural interpretation. I mean, if you observe the Himalayan ranges, you will see the mountain belts are all striking east-west, and they have a very systematic distribution of height, and they also show some folded structures, some faulted structures. So all of these things can have some implications over the topography, and that is why when you just see the geographic map of a region without having a geological map, then also you can infer, okay, so there might be some geological processes, especially some tectonic processes, that are giving rise to this kind of features we generally see from a geographical map, right? So understanding understanding geological map of a region, what you do learn from a field geology course. Then the important part is handling field measurements, or and some practical aspects of measuring structural attributes. Right. So this is one of the important factor especially the right hand rule. So this is very important because you see, measuring deep strike, pitch, plunge, trend, whatever you have in your exposure, whatever structures you are trying to see, first of all, you get to look into the structure, what it is, and then you have to take measurements. Right? So for taking measurements, you have to first identify the features, right? So say for example, in the Ferryghat location, there were some beautiful exposures where you could see the striping lineation and bedding cleavage intersection. Like, so these kind of tricks are generally helpful for getting a big picture of a region. Like, because any of those bedding plane and axial planar cleavage intersection would ultimately give you the fold axis of that region, right? If the region is at all folded, right? So these kind of interpretation. So another thing is understanding which is a bedding plane. I mean, which are the bedding planes in a field, right? In a metasedimentary terrain, identifying bedding planes are very tricky things. And then there are some tricks, like understanding the compositional banding, then seeing the thickness variations, right? So these kind of things are helpful for distinguishing between what has been uh, derived from a mechanical point of view, right? Like these axial planar cleavages, they originate generally from deformation, which are different from bedding planes because they are not so much systematic, and they have variations in their thickness and also their composition, right? So what we call in terms of sedimentary geology is the facies. So different facies will have different rock types, different grain sizes, and different sedimentary structures, and also different compositions. All of these things will somehow tamper with the deformation, and eventually it would result in different structures. Even you could see cleavage refraction, right? Because some beds are rich in quartz and feldspar, which are more quartzo-feldspathic in nature, and therefore they would divert the cleavage from other bedding planes where mica is more abundant, right? So all of these things play a very important role while trying to delineate the structural features, and working smartly would save your time. And in that aspect, right hand thumb rule for measuring the deep and strike orientation are very much helpful, right? And even you have seen that in one video I have explained that how, despite having a very low angle tilt in the surface, you can generally use the water level for understanding the strike direction, because water will always be, the free surface of water will always be horizontal, and you can leverage that fact to get the strike line of a very low dipping bed, where your Brunton compass or clinometer would not work, because they are instruments and they have certain resolutions and their precision, right? So these kind of tricks you would learn, and these will come from experience. The more you go to the field and do structural geology field work in different deformed terrains, in complex terrains, in simple terrains, in terms of deformation, you would learn more and more from your experience. But to start, these are some helpful features you could easily use to get the structural data. So this was one of the major aspects in the field structural geology course. The third point is obviously understanding polyphase deformation. polyphase deformation in a regional aspect, and fourth is understanding superposition of ductile deformation, and then obviously brittle deformation, which includes distinguishing distinct distinguishing faults and joints, and even you got the exposure to see semi brittle deformation. If you remember, that was from the gash fractures. And obviously strain analysis in shear zone. So these are some takeaway points or learning points from this course, Introductory Field Structural Geology. And we have thoroughly discussed some conceptual multiple choice questions regarding these individual topics. So we have discussed about geometry and structural attributes in the first session, then talked about uh, brittle deformation, ductile deformation, mechanism of folding, and problems related to them. I mean, these topics. And we also finally talked about lithostructural mapping and inferring geological map, and how we actually apply these techniques to understand um, the stratigraphic disposition of different units, right? So all these things were discussed, and now in this extra or this additional problem solving session, I would request you, so that if you have any doubt regarding any of these topics, so you can feel free to mention, and we can have some discussion on those things. And other than that, I have a few topic in mind, especially strain analysis. This is a very important topic. I found that it should have been discussed extensively, uh, because three-dimensional strain analysis is very much important when we have put a lot of focus on that. But other than three-dimensional strain analysis, there are also parts of two-dimensional and one-dimensional strain analysis, which are also very much important for your understanding. So I will obviously discuss these aspects of one dimension and two dimensional strain analysis in this section, in this session. But other than that, I would give you some time to think, that if you have any doubt regarding any of the sessions or the course in general, you can ask me, and hopefully I would be able to answer those questions. And then if not, then I will proceed to explain some aspects of strain analysis. I guess it would also be helpful for your further endeavors in field structural geology. So I will just pause for a minute or two, then let you think, that if you have any doubt, you can skim through your lecture notes or your topics, and if you want to discuss anything, then please bring it up, and we will be having some sort of discussion. Okay. Okay, then I should move further for today's discussion. I'm assuming that you don't have any specific doubt regarding any of these live sessions or the course in general. So I would be talking about strain analysis. So strain analysis can be done in three different modes: 1D, 2D, and 3D. Right? So one dimensional, two dimensional, and three dimensional strain analysis. You have been told about the three dimensional strain analysis, and it is very much important for understanding the kinematics of a shear zone, especially if you have strain markers. Then you would be able to understand uh, what is the overall uh, type of strain, whether it is plane strain, constrict constriction, or flattening strain. Right. So these are the typical three classes in which we distinguish three-dimensional strain, and we generally do that using a Flynn diagram, right? So the overall concept of tree diagram and how it is calculated, they are extensively explained in the lecture videos. But I think that we should also be focusing on 1D and 2D strain analysis, right, in this discussion session. So when we talk about strain analysis, you should always keep in mind that in theory we can learn about progressive deformation or progressive strain, but in practicality we cannot measure progressive strain, but we only measure finite strain. So finite strain means the total deformation accumulated over time. It is as simple as that. That means you just get to see the final result. Now there is an important limitation when we are inferring that this is the final result. So to get a final result, you need an initial reference, right? But the challenge in geological deformation that we do not know what was the initial reference. So final result without the knowledge of initial reference. We do not know that. And therefore, we impose some geometric assumptions. And therefore, and since we are imposing some geometrical assumption, we can, I mean, we most definitely cannot actually say how the deformation took place, because we do not have the information about the initial reference. We are just only observing the final result, and we do not know what is the path of the deformation, right? So say for example, I have a destination A and I want to go to another destination B. The simpler way is to go straight, but we can go like this or like this, or any way seems favorable like this. Each of these paths, say if I say 1, 2, 3 and 4, each of these paths would result in a same destination, but we do not know how much time did it take, and therefore we do not know how fast or how slow all these processes were. And obviously, depending on the path, we also do not know how the progressive change took place, right? So we cannot comment on the path of the deformation. It is not possible for us to actually encounter any of these paths, right? The different paths are therefore assumed to originate from different initial geometry. Okay, that is how we make an assumption that, okay, so if I have object A, B, C at different stages, and if all of them result in a same deformation and the final object is D, then for each and every of these initial objects, the path of deformation would be different. That is why they are resulting in a same object. And the logic is that, so if A, B, C are different objects initially and they took the same path for deformation, then obviously they would result in different objects after deformation. But since they are all converging towards the same deformation, that means that the path has to be different for all of these different objects, different initial objects. So that is why we put this assumption a priori to the initial geometry, and we infer subsequently so which in which category or in which path the deformation has taken place. Okay, so that being said, there are some strict rule of thumbs, or you can say primary assumptions about how we impose this how we infer the initial object, right? Because if we assume all of the objects are irregular in geometry, then we will never be able to understand how the deformation has taken place. So for reference, we need something which is geometrically simple to actually infer. So that is the main point. Because deformation, when you go to the field, you see that obviously it is very much heterogeneous in terms of scale, and anything can happen over the million years of time. The deformation has been accumulated, and that can go on to several different paths, and ultimately the result would be so much complex that the geometry is alone is pretty much difficult to tackle. Then again, if we impose that the initial geometry was also very much complicated, then we could not even analyze how much deformation had taken place. So because of that, we impose certain rules in which through which we actually simplify the initial geometry in reference to the deformation. So these geometry, in terms of strain analysis, we call them strain markers. And strain markers have a definition and some criteria which will fulfill the definition of a strain marker, and eventually we will call that object a strain marker. So now we should define what is an ideal strain marker. So strain markers are natural objects with well-defined initial geometry, or we can say undeformed geometry, which can be utilized to estimate the strain accommodated in a deformed strain accommodated in a deformed particle or an object in a rock assemblage. So this is the definition of a strain marker, which says strain markers are natural objects with well-defined initial or undefined geometry, which can be utilized to estimate the strain accommodated in a deformed particle or object in a rock assemblage. That's it. And we also say there are at least 5 to 6 certain criteria for identifying a strain marker. So the first one is originally spherical or equidimensional form. Okay. Such as ooids, reduction spots, some microfossils, such as foraminifera or radiolaria, right? Some igneous rock textures. So these all are examples of originally spherical or equidimensional form. The second one comes as original circular cross section on a known surface. So like pebbles in sedimentary units, rain imprint structures, sin sedimentary deformation features, such as convolutes and also some ichnofossils. Third one is originally elliptical object. So pebbles from sedimentary units and especially conglomerates are originally elliptical in form. So they can serve as ideal strain markers for initially elliptical objects. Right? So pebbles and conglomerates and ooids can be originally elliptical in shape. Right. So other than that, there can be original linear form. Right. There can be several fossils which can become linear. For example, belemnites. These are cephalopod fossils. They have a very typical cigar-shaped structure, exoskeleton, which is essentially considered as one-dimensional or linear objects that are helpful for understanding one-dimensional strain accumulation, particularly in uh, region where tension and shearing has taken place. So you all know that depending on the orientation of the strain ellipse, shear deformation, in terms of simple shear deformation, can induce compression as well as tension, because it can either get compressed or in the perpendicular direction it can also get stretched. So for any stress field where there is a stretching or a stretching is a component, there will be breaking of these belemnites, and they would serve as essentially Boudin structures. So Boudinage is also one of the important features that tells us about the, you know, that the term is the instantaneous stretching axis of the finite strain ellipsoid of that particular region which you are trying to infer the strain. So the instantaneous stretching axis of the finite strain ellipsoid will be parallel with the long axis of these belemnites or linear fossils, and they would easily get stretched apart and they would be severely boudined. And this boudinage would result in fragmentation of individual of these fossils, and therefore once you see these kind of structures, you would definitely consider them as strain markers. So belemnites are examples of such linear strain markers, and then again there can be sections of cross stratification. So cross stratification or ripple marks, right? You know that current ripples in particular sections they would form these linear structures, and their deformation would generally uh, would change the shape. So it would be originally linear and then it would be changed to something which is not linear. It can be either folded or it can be stretched apart to create budins, right? They can also be compressed to create folds. So all this kind of, or they can also be faulted. So the idea is that these particular features, they are not originated from deformation. They are basically sedimentary structures. So they can serve as linear strain markers. So and then bilaterally symmetrical objects. So brachiopods, trilobites, echinodermata. So all these are bilaterally symmetrical organism. So this helps us in understanding the simple shear component of a deformation. Right? This part is important. They are essentially helpful for understanding the simple shear component of deformation, or we can say non-coaxial. Component of deformation. So this is something which is known as bilateral symmetric objects, right? And the final category is that even if you do not have any uh, proper shape, right? It can either be a polygonal structure, right? Say for example, mm, grains. So if you make a thin section, so say for example in igneous rocks, you won't have all the luxury to get these fossils and rain imprints and sedimentary structures as your strain marker. They won't be available in igneous rocks. So then, how can you get or estimate strain and accumulation in a rocky terrain which is mostly of igneous rock? So that brings us to the last and the very fine, I mean, very important strain marker or important initial reference is known initial angle. Say, for example, I have some euhedral grains, perfect hexagonal shape. This kind of structure is present, and then I deform them. I have I mean, normal component like this, and I have a shear component like this, and eventually they would turn like this. After deformation, say for example, this is how it is changing. Now for that igneous rock, these angles are known, right? Or this entire internal angle, we know these angles, right? Say for example, if this is a triple junction, then this angle obviously is 120 degrees. So these are some features we rely on, even if the object, the strain marker that we are considering, is not of simple geometric shape, because polygons are not simple geometric shape. We either have to have some circles or spheres or lines, or even, say for example, a square for say, or a rectangle, right? But other than that, we just have to rely on the angle. So these euhedral grains are such examples of initial known angle which can ultimately mm, provide us some means of calculating the, I mean, the total accumulated strain, which which is obviously a combination of both pure shear and simple shear. We cannot just delineate one from the other, but essentially these would help us in understanding the overall strain accumulation in a rock. So this is one feature. Other than that, we can also have cross beddings. The angles in a cross beddings are particularly constant if you make, or if you keep the energy condition of the fluvial environment constant. So you can have the cross beddings. You can obviously have mud cracks. Then you can have these prismatic crystals, prismatic quartz crystals, preserving the euhedral angle. So these are certain strain markers, I mean examples of strain markers that can ideally be used to uh, interpret the amount of strain, right? So now if we talk about two-dimensional strain analysis, we have two important methods. One is center to center method, or also known as Fry method, and the other one is RF phi method for strain measurement. So if I just describe what is the practicality of these two different methods. So first of all, let us discuss about the Fry method. So the idea is that say for example, I have this block and I have certain spherical or some points, right? Now, if I just want to connect the centers between each of these points randomly, these, 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 or these. So I can have, I mean, a number of combinations like this, right? Through which I can connect the center points of these randomly distributed spherical or circular objects, whatever, in this entire region. So now if I just compress the material in a pure shear mode, or even if we just compress from all the sides, but there is difference in the stress, say for example this is sigma 1, this is sigma 3, obviously this would flatten and this would stretch. Now what will happen is that if these markers are rigid objects, that means they are not rotating or deforming, but just the material surrounding matrix or the material is flowing. So if that is the case, so what will happen is that there will be a preferential direction along which, so if this is compressed, so all the, I mean, directions measured parallel to sigma 1 would reduce the length, the length between centers to centers parallel to sigma 1 will decrease and the lengths, or we can say the distance, parallel to sigma 3 will increase, right? Now if this is the case, then if I just plot the distances from a central point of view, then I would see that initially my distribution of the distances from a central point is random, and therefore it is homogeneous. But then after deformation, I would see certain distances are getting reduced from the center, because points are moving away. Now the void space will generally be representative of the how much flow has taken place. So if we consider a central point of reference and measure the distances away from it, the void space surrounding the center will be proportional to the deformation. Right? Now, if that is the case, then for a deformed assemblage of points, will create a void space in the shape of the strain ellipse. Right? So this is the theory. So how, I mean, then how do we measure the strain? Say for example, I have a region where there are several strain markers. Right? Now, what I need to do first, I get a tracing paper. So and using the tracing paper, I first reference the tracing paper with respect to the markers. And then I pinpoint a central point uh, of that tracing paper, I mean of this referenced area. So I should draw just diagonals to get the center. Now bring that reference point, I mean from the tracing paper, to any of the strain markers center. Right. So you bring it, say for example, I place this center, say for example on this marker, I have its center point. So align this center point with this tracing paper center point. And then simply mark the center points of the other markers. So it would translate in this tracing paper like this. You would get points like this on the tracing paper. Mark the centers of other markers on the tracing sheet. Right. So you will eventually get some points. Now the thing is that reiterate this process for all of these markers. And then finally what you will have is that on the tracing sheet, you would get distributions of points like this. So if you have enough markers present there, you would find that based on the center, you have got a void space which generally looks like an ellipse. So if you fit the best fit ellipse within this void space, we will get the strain ellipse. So this is the process how you actually determine the strain ellipse, the finite strain ellipse. So for example, in this method, we determine the finite strain ellipse of the deformed rock and once you have the ellipse, you can measure so the ellipse has a long axis and a short axis. So measure the and the short axis of the ellipse to mm, calculate the aspect ratio. So the aspect ratio is basically we represent aspect ratio with R. Aspect ratio is basically the ratio of the length of long axis and short axis. And interestingly, the long axis is the instantaneous stretching axis of the strain ellipse, and if you measure the angle, say for example theta, so if you have north, I mean your direction on the plane you are measuring, you can measure the angle with respect to the coordinates. So the angle between geographic coordinate and the ISA, ISA max, this is ISA max, will provide us the direction of sigma 3, right? Because you know that if strain ellipse forms, then obviously the short axis will be parallel to sigma 1 and the ISMX will be parallel to sigma 3. I mean, not parallel to exactly, but it will be subparallel to or at low angle with respect to sigma 3. So in this way, using two-dimensional strain analysis, we can actually measure how stress fields were oriented during the deformation of the rock assemblage. So Fry method is very much helpful in understanding how the rock has, I mean, flown. So it is essentially restricted for ductile deformation, because in ductile deformation only you can get the flow path of the rocks, right? The velocity path and the flow path of the rocks. It assumes that the strain markers are ideally rigid objects. They stay put within the or embedded in the matrix, and the matrix is basically flowing. So this is essentially important because in this case we are neither considering we are not considering any of the geometric feature of the objects itself. So it can be elliptical, it can be circular, it can be polygonal, whatever it is. If it is a two-dimensional object, then it has to be there has to be a center, and we are just considering the center because we are measuring how these center points are actually moving away from each other. Now the thing is that whatever strain you estimate, this would obviously be an underestimation of the true strain, because here we are considering that objects are ideally rigid and they are just only flowing with respect to the matrix, right? And the distance between center to center is increasing, but in reality that does not happen, because in reality the objects will deform too. Even if it is a rigid object, there will be rotation involved for each of these individual strain markers embedded within the matrix, and therefore due to the rotation they will also accumulate some shear strain, I mean angular strain. So that is not estimated in case of center to center or Fry method, and that is why we are also not estimating the individual shortening of this uh, elliptical or whatever the initial geometry is. We are not also considering the shortening or stretching of these individual markers, but we are considering the markers as a whole, and the entire assumption, the entire process of strain calculation or strain estimation rather, is based on the fact that we are considering them as rigid objects embedded within a flowing matrix. That means there is a competency contrast between the strain marker and the surrounding matrix. If if that competency contrast becomes low, then you would not be expecting to calculate strain or estimate the finite strain from this method. Then you have to rely on some other processes, that involves further intricate analysis of crystal plastic deformation in case of materials which are undergoing metamorphism, say for example mica schist, right? So that being said, so granulation cleavages and all these things are developing just because there is a heterogeneity in the composition, and obviously those deformations occur in a very high pressure and high temperature regime, and in that high pressure high temperature regime there will be obviously some crystal plastic deformation mechanisms. So you will learn about the crystal plastic deformation mechanisms in your probably in your postgraduate courses. So in case of crystal plastic deformation, the lattice of the crystals distort and they individually accumulate certain strain before going on to the large scale or bulk scale strain accumulation. Right. So even if you get a granite in which you cannot see macroscopic features like folds and faults like that, you would definitely find lineations and foliations within that granite that would say that the granite is deformed. And when you make a thin section from the rocks, you would see that the individual grains of the quartz and feldspar, all these things are deformed. And from that, if you do further analysis using some diffraction methods, some analytical methods would give you the estimation of a strain that has entirely been accumulated through the plastic deformation of individual crystals of the rock and individual crystals of the minerals present in the rock. And that is entirely different from the macroscopic strain, because a large part of the macroscopic strain has been already been accommodated through these methods, and the remaining part becomes feasible in the macroscopic processes, such as forming a fold or shortening of some layer parallel shortening, like things that and then faulting, and then the rotation of the rigid objects in a matrix, say for example the rotation of porphyroblasts and porphyroclasts, and these kind of things takes place after there are crystal plastic deformation, right? So these are certain features which help us understanding or I would say that uh, gives us a better estimation of strain rather than just relying on these features. So these features, that means that disposition of marker, is very much helpful if you have some macroscopic feature. Macroscopic features means either you have to have some visual evidence from your hand specimen or outcrop scale, or you have to rely on the geodetic data in case you are trying to understand the geodynamic scale features, like collision between Indian and Eurasian plate and how the Indian plate is undergoing deformation, I mean progressive shortening because of the rise of Himalaya and all these kind of things. They involve the measurements on these GPS and geodetic stations. But other than that, if you have some folded material or faulted material or brecciated material, bodinized material, rotated material, I mean these kind of things, which was initially circular then turned into elliptical, and they have preferred orientation, from there you can have a gross estimation of the finite strain accumulated over the time. And obviously you can get the orientation of the strain ellipse, the finite strain ellipse, the maximum instantaneous stretching axis, which will be somewhat related to the sigma 3 of the stress field during the deformation, and eventually you can derive what would be the maximum compressive stress regime for that particular region. So these kind of methods are useful, particularly for understanding ductile deformation. For brittle deformation, there are other features we use for strain analysis, especially balanced cross section in shallow crustal materials is a very good way of estimating the overall shortening in a fold thrust belt, right? So there are in number of different ways we could analyze strain, but 2D strain analysis that I talked about, it is essentially restricted to some outcrop scale features. So if you go into the field and see that imbricated structures, distribution of pebbles, or some strain markers which are derived from deformed fossils, you can easily apply these methods for understanding, particularly for that outcrop, how the instantaneous stretching axis of the finite strain ellipse has been oriented with respect to the geographic coordinates. And then you can have an estimation of the aspect ratio. That means how much strain is being accumulated. That's it. So with that, I end today's discussion session. So I hope that you learned something about strain analysis and some practical methods and guidelines about using some markers for strain analysis. So I hope that you have understood well about all the materials from the course, which is this introductory field structural geology. And if you have any doubt, you can always reach out to me personally. I can also provide some help or guidance regarding any topic if you have any confusion. So with that, I am ending today's discussion session and hope that you perform well in your examination for this course. And thank you. Bye.